Good afternoon, everyone, and welcome to the SMI Lunchtime webinar. As all of you, I'm sure, are aware, today is World Day for Safety and Health at Work, and therefore it gives me great pleasure to welcome Nikky LaBranche, who's our Research Manager for Occupational Health and Safety, an inaugural industry fellow in the Mineral Industry Safety and Health Center, MESH, at the Sustainable Minerals Institute. Nikky will be discussing her work on particulates and mine dust lung disease. Sorry, Nikky, I got that wrong. And as you know, coal workers' pneumoconiosis made a reappearance in Queensland back in 2015 after a gap of about 30 years in the diagnosis of new cases. And Nikky's going to talk about the gap analysis in the recent history of mine dust lung disease in Australia and aspects related to mining. As per the previous one, once we are finished with the presentation, there'll be an opportunity for questions. And at the bottom of your screen, you will see a tab that says Q&A. Please feel free during the talk to post your questions there. And then at the end, I will then pass on those questions to Nikky. So over to you, Nikky.
Okay, well, thank you very much. So we'll be talking about removing some of the unknowns in respirable dust today, and this is work I do at MISC in conjunction with David Cliff and Brett Garland. So I'll start off with a few acknowledgements. So this work actually started as an ACART project. And that was a gap analysis of basically what were the new research initiatives that needed to happen. And since then, we've gotten input from, financial support from Glencore Copper, from Peabody, from the DNRME and SIMTARS, and from the University of Queensland. This project has also had technical input from Fritz Dukic, Greg Manthe, and Eliza Gill at the DNRME, from Coal Services in New South Wales, from Mark Shepard and Lucas Boyne, and from Barath Bell from Anglo, who's the ACART monitor on this project. So the agenda, so I'll introduce a little bit of history to you and some definitions, talk about what we do to control dust, talk about some of the dust monitoring devices, and then about particulate characterization, which is the substantial portion of my work. So a few definitions for you. The respirable particulate fraction, or respirable dust as I'll refer to it throughout the presentation, is that fraction of inhaled particulate that can penetrate beyond the terminal bronchioles into the gas exchange regions of the lungs. So it's that dust that gets deeper into your lungs that we're concerned about in the respirable fraction. The other term you need to know is mine dust lung diseases, and those are caused by long-term exposures to high concentrations of this respirable dust that's generated during mining and quarrying activities. So while we typically thought of coal workers' pneumoconiosis as the main lung disease from mining, there's also mixed dust pneumoconiosis, silicosis from the silica dust, which is now coming more to the forefront. There's chronic obstructive pulmonary disease, which is an umbrella term for occupational asthma, chronic bronchitis, and emphysema, as well as asbestosis. So there's a range of mine dust lung diseases that can happen from working in the mines. And as we manage these occupational health issues, such as dust, we should be looking at them the same way that we manage workplace safety. But historically, this hasn't been the case. And I'll explain a little bit more as to why we should be managing this way. And to do that, I need to walk you through a few more definitions. So bow ties are one of the tools that we use to visualize the control of dust disease. And we want to look at the control effectiveness from them. So what are the controls? How effective actually are they? How can we measure them? And what can make them ineffective? And we also want to look at some of the intrinsic assumptions that we have about the dust and what may not be actually true. With that, there's been a lot of things with the dust that it's been years and years. So some of these were done in the 50s or the 70s, and we've been relying on the same assumptions, and the science may be better now. So what still holds true and what was just a generalization. So this is the bow tie for respirable crystalline silica. And the blue on the left are the sources. The orange in the middle is the unwanted event, which is the hazardous concentration of dust buildup. And the red on the right is the consequences of this dust. So next to the blue and the white boxes are the preventative controls, and next to the red on the right-hand side are the recovery controls. And while for most safety issues, we actually monitor those controls themselves and make sure that our controls are working to manage safety issues, that's actually not what we're currently doing for respirable dust. We holistically monitor personal exposure for the whole of shift. We don't monitor the effectiveness of those individual controls. And when those aren't being monitored, we don't know how these controls are performing. So in 2015, the first case of coworkers' pneumoconiosis was reported to the department in 30 years. Prior to that, they didn't think they had a problem because there was nothing being reported, but they'd actually gone back and found a few older cases, as you can see on the far left, as well as when they started looking and redoing the health surveillance scheme, a number of more cases came to light. And as you can see with these cases, only about a third of them are coworkers' pneumoconiosis. That's the CWP in the teal. The vast majority of them are actually a mix of different dust-lung diseases. And so with this host of dust-lung diseases we're now dealing with, the assumptions that we have were all based on coworkers' pneumoconiosis. So we've got to go back and look at some of these underlying assumptions again from a more holistic approach to all the dust-lung diseases. So originally, the data was based back on the British pneumoconiosis field research data. And this told you at 1 milligram per meter cubed of exposure every day for 40 years, these are the percentages of the mining workforce that would have different grades of CWP or PMF, which is progressive massive fibrosis, for the different ranks of coal. And basically they were looking at what was an acceptable amount of people getting the disease at these different levels. But a lot of things have changed since then. So the mechanization in the mines have changed. We're dealing with different coal seams. So we really need to go back and look at what is true now, and do these assumptions still hold true? The other factor was that there's one glaringly obvious part missing from this older data, is that they didn't actually take into account the silica that was present in there. They were only worried about the total dust. And we now know that silica is it's very fibrotic and can lead to silicosis and other mine dust lung diseases, so that we really do need to look at what is that silica content of the coal dust. So that is an important factor that wasn't necessarily taken into consideration then. So as part of this, we've looked at the historical dust in Queensland and the compliance sampling that's been done. And as you can see here, these are the percent exceedances at different levels. So the blue line is the percentage exceedances that happened at the 3.0 milligrams per cubic meter standard, which was the case for Queensland up until last year when the standard changed. So you did have about 10 to 20% of the samples that were being taken above that standard. But as you can see on the red line, the number of samples was very low historically and has only recently gone up. But if you look at a lower standard, for instance, the 1.5 milligrams per cubic meter or the 0.09 milligrams per cubic meter, you can see that at those levels, there would be a higher percent exceedances there. And the coal dust exposure level has been reduced to 1.5 milligrams per cubic meter recently. So this will be the new standard going forward. And at that level, you can see that if that would have been the historic level, somewhere between 20 and 50% of the samples would have not been in compliance. And we see a similar issue with the percentage exceedances for silica. So the old standard was 0.1 milligrams per cubic meter, and the proposed new standard was the 0.02 milligrams per cubic meter in the purple. But Safe Work Australia has decided to go with the 0.05 milligrams per cubic meter, which is the orange level. So you can see that there's still be a number of historical exceedances at that level. And part of the reason I'm showing you this is that these are long latency diseases. So even though we've decreased the exposure standard going forward, you do have people that have been in the mines for the past 20 years that have been exposed to these higher levels. So you will have future disease diagnosis from that exposure. So just making the exposure standard lower today, there'll be a lag between that and the disease rate starting to go down. So with that, we need to look at controls and what actually is a control. It's actually trickier than you think. A control is an act, object, or a system that directly arrests or mitigates an unwanted event. So a signature or a piece of paper is not a control. Control is specifiable, measurable, and auditable. And we need to look at, how do we assess these controls? How do we know they're effective? And what things could be happening that could prevent these controls from being effective? And there's a whole host of controls that mining is using. And here's a list of some of them from the workshops that we've done. And as you can see, there's a whole host of things there, but they weren't necessarily being used to their full ability. So for instance, sprays may exist on equipment, but you have to actually keep the sprays in good working order. So keep them from getting clogged, making sure that there's enough water going to them, also making sure that they're the right size for the dust that's present. There's other new things being tried, like the application of foam, increases in automation to get the people out of the area, as well as using more monitoring devices to see if these controls are working. So with sampling, all the compliant sampling is currently done gravimetrically with a cyclone elutriator and a sampling pump. And these are worn by the miners for the duration of their shift. So in Queensland, that's portal to portal. So for underground, when you go into the mine versus when you come out of the mine, slightly different for New South Wales, where it's crib room to crib room. So they're already down in the mine when they start the sampling. So it's for a slightly shorter period of time during the shift. And so the pump draws in air through the cyclone to approximate the breathing rate for the miner and collect a sample of dust on the filter. And this filter is then weighed in the laboratory. And there was an issue with one of the types of cyclones in the flow rate was at 2.2 liters per minute, and it was found to be oversampling by about 30%. So that data needs to be adjusted, but because the particle size fraction is different, there's no linear way to adjust that. You can't simply divide it. So all the historical samples are slightly off. So they've had to increase the flow rate to be able to compensate for that going forward. And the blue bars show you pre and post that change in flow rate, what the concentrations being measured were. So they do show a decrease in concentration post the change in flow rate there. And with those, I was actually taking some characterization samples before we found this out. And looking at them, I had a large percentage of the particles I was collecting greater than 10 microns, which you wouldn't expect to see more than a few particles over that size. So it was a bit concerning to see so many large particles showing up. There's also real-time monitoring devices, and there's several different technologies for these. The first one here is the Thermo Scientific PDM 3700, and that's a TOM technology, which is a tapered element oscillating microbalance. And with that, you have a little platform in there that the dust collects on a filter, and a magnet underneath, and the oscillation of that magnet determines how much mass is on there. So this is a mass-based unit that will give you 15 and 30-minute average concentration. So this is something that a miner can wear underground and look at how much dust they're currently being exposed to and see their cumulative shift concentration. And that allows them, if they see the concentrations they're in are currently high, they can start to do something about that and take a proactive approach to ensure that they have a lower concentration and don't exceed their maximum allowed concentrations for the day. The other device here is the TSI AM520, and that's the only real-time monitor that's currently approved as intrinsically safe for use underground for IECEx. And this device uses light scatter, so it's measuring the amount of particles that go across a laser beam. So it doesn't actually look at the density of the particles. So you can use light scatter for an approximation of how much dust is there, but you can't use it for a mass-based measurement that they're currently using for compliance. But tools like this can give you down to the second dust level measurements. So they are ideal for use if you're looking at point source and levels. And really, if the certain cycles or certain processes are generating more dust, or to see if your controls are working for those dusts, and compare and contrast. And so with the PDM, there are issues with the current filter for quartz analysis. So it uses a borosilicate filter, which cannot be ashed currently. So while you could get a mass-based measurement of the dust, you couldn't get a silica measurement off of the same filter as you can the gravimetric filter in the lab. So there is work being done on those to be able to use nylon filters. And if you change to a nylon filter and then change picture B, which is the plastic plate underneath the filter, if you change that as well, you could actually use diffuse reflection spectroscopy to be able to get a quartz measurement off of the filter. So that is something that they're currently looking at, adapting that technology, and that could be done at the mine site rather than what's currently done with the gravimetric filters, which is they have to be sent back to the lab, and it can be 2 or 3 weeks until you know if the if your sample was in compliance for the shift or not. This way, with a real-time device like this, you definitely know your dust levels at the end of the shift, because you'd have them the whole time during the day, and you could get a printout as you came up from underground. But with them working these issues out, you could also get your quartz levels as well. There's also a few other devices that are used in Australia as well. So there's passive light scatter devices. So the first one here is the HUND TM Data 2, which is used by coal services, and the Thermo Scientific PDR 1000 AN, which is used by Simtars and by some of the mines here in Queensland. And these are both passive light scatter devices. So you basically, the dust cloud passes over the laser, and it just measures the amount of dust in the air. Again, there is no density measurement here, so it's not mass-based. It's simply a measurement of how many particles are present in the size fraction that you're looking at. The other complicating factor with these, as well as the TSI that I spoke about previously, is that for the light scatter devices, they'll also pick up water droplets. So you can't be doing measurements in areas where you have high presence of water droplets, or the numbers you're getting won't actually be indicative of what the dust levels are, because you're also measuring the water. Okay, so far I've talked about the respirable curve, which is that second one from the left there. But there is several other particle size distributions that we also need to look at. And those are leading to some of the host of lung diseases that are out there. So we're starting to look more at the ultrafine particles, and in the smaller size range, and the large numbers of those there are, as well as some of the larger inhalable particles, which the research is pointing to relates more to the COPD diseases. So with that, I'll give you a little bit of a math lesson. So with those respirable particles, the 50% of them so the D50 is 4 microns. And so that's the middle size range is 4 microns for those respirable typically. But if you look at some of the ultrafine particles, they may be closer to the 0.4 micron range. And if you look at the differences in the sizes there, so the volume of one 4 micron particle is equal to the volume of 1,000 0.4 micron particles. So if what you're measuring is the mass of a particle, and you have that one 4 micron particle, that's a significantly larger percentage of the volume than having a few 0.4 micron particles would be, even though those smaller particles may actually be contributing more to the health hazard. And those smaller particles would also have a much larger surface area than that one larger 4 micron particle. And I'll show you this in the next slide. So this is a comparison of the count of particles versus the volume of particles on some of my characterization work. So as you can see, for the count, the blue, which is most of the particles, about 2/3 of them, are less than 2 microns. And in fact, this methodology cuts off at slightly less than 1 micron, so that you're only really looking at 1 to 2 microns in that blue, where you can see the count of particles greater than 10 microns is incredibly small in the yellow there. However, if you look at the volume that those particles account for, that very small number of greater than 10 micron particles actually accounts for a large portion of the volume, whereas that large number of particles less than 2 microns is an incredibly small portion of the volume. So the intrinsic assumption we have about the mass of the dust being related to the health hazard, and that's how we measure compliance, doesn't necessarily hold true. And in fact, there's been some research done with lung tissue. So this is a study on the left-hand side that was done by NIOSH in the US, looking at the different reaction of lung tissue to different size silica particles. So the red line on the bottom is the coarse particles, which is a median size of 4.1 microns, and the blue diamond above it is the ultrafine particles with a median of 0.3 microns. So as you can see, there's a lot more reactivity, which is measured by fluorescence over background from the alveolar macrophage activation of the particles. So a lot more reactivity from smaller particles. So this needs to be factored into how we look at how we're measuring the health hazard. So, and the University of Cape Town is looking at inhalable dust on lung tissue, and David Waite down in New South Wales is looking at respirable dust on lung tissue. So there is some of this work going on. And there's two aspects of mitochondrial reactive oxygen species pathology. So, and that's what I'm showing you on the right-hand side. So the first is damage to the mitochondria, which leads to cell death. And the second is the redox signals. So if the redox signals are disrupted, i.e. there's too much or too little redox signal, that may cause chronic disruption to the cell signaling pathways. And this is what David Waite is working on at New South Wales with the redox active metals and focusing on bioavailable iron there. So not only does size make a difference, but there's also issues of geography and the coal seams that make a difference. And the US is a great example of this. So they've been tracking their pneumoconiosis cases for significantly longer. So the graph A on the left is all of your US underground coal mines and the level of the prevalence of coal workers' pneumoconiosis that's being recorded. Graph B is Central Appalachia. So you see if you take Central Appalachia out of the whole US, they actually have a much higher prevalence rate. So 20%, 1 in 5 miners that's worked more than 25 years in the coal mines has coal workers' pneumoconiosis. Or if you take out Central Appalachia, which is graph C, you can see that in the rest of the US, the level is very low, only about 5% or so. And this held true for the old UK mines as well. So different counties had much higher prevalences of CWP than others. So this has caused the US to start to look into the characterization of the dust as well. And this is a comparison of the chemical components of dust in 8 of the mines in different regions of Appalachia. So mid-central, northern, and south-central Appalachia. And one of the interesting things that you see here is that the blue, the carbonaceous, which is your coal and your diesel particles, are actually very low in many of these samples. So surprisingly little of your quote unquote coal dust is actually coal. You have much larger proportions of aluminosilicates, of quartz, of carbonates, which in a lot of cases is your stone dust that they're putting on the walls, and a few heavy minerals and a few other elements in there as well. So I'm doing similar work here in Australia to look at what's happening in Australian mines and what the composition of our seams are. So besides the composition, the particle size distribution is also very interesting as well. So this is the cumulative particle size distribution from that US data I just showed you. So the 1,000 nanometers in the middle there is 1 micron. And as you can see, most of the accumulation of particles is happening in that less than 1 micron size. And by the time you get to 2.5 microns, you've accumulated pretty much all of the particles there. And that's another interesting thing. So where with hygiene, we're looking at the respirable fraction and that D50 of 4 microns and up to 10 microns. Environmental looks at the PM 2.5 and the dust smaller than the 2.5 micron size. So I think for coal, we need to start taking a look at the smaller size distributions as well. Another interesting thing we found is with the diesel. So as I mentioned before, the methodology that was used can't tell the diesel from the carbonaceous with the scanning electron microscope with XRD. But if you actually physically look at the filters, because the diesel is a different shape, you can tell what's diesel and what's not. And some of those particles are actually agglomerating into larger particle sizes. And as you can see, we've gotten the one in the bottom middle is as large as 2 microns. So that's a very interesting finding on there for the diesel that's collected in the mines, because we typically don't measure environmentally for diesel. Most of that work is done at the source. So there's the filter on the machines and it's measured there, not in the ambient air. So this presentation has focused on coal mines, and that's because there's a lot of information available on the exposure risk for coal miners to respirable dust, and they're starting to be for some of the other size fractions. But a lot of this will apply to quarry workers and to metalliferous miners as well. It's just that situation is a bit more complicated because unlike in coal, where there's robust health surveillance programs and all miners have health screenings and chest x-rays every few years, there's no centralized comprehensive medical screening program for the quarries and the metalliferous miners. There's also no industry-wide tracking of exposure data until 2018. And even for the coal mines, while they were required to keep the exposure data for 30 years, when they were asked for it by the government, there was a lot of work that had to be done by some of them to bring it all together into a usable format. And mines that had gone out of business in the last 30 years, a lot of those records have been lost. And there's also no tracking of respirable dust-related illnesses in the metalliferous sector. And also in the news, you may have heard about the stone benchtop workers, and that's exposure to silica, and that's very high levels of silica. And with the cutting that's being done, very small particle size fractions as well. So that's another related exposure to this. Okay, and that's all for me. Thank you.
Hi, Nikki. Thank you very much. All right, so the question and answer session is now open, and I will read through those questions as they come through, and then hand it over to yourself, Nikki, if that's all right. So we've got one here. Where do non-asbestos fibrous silicate minerals fit into the list of threats just shown? So this must have been quite early on in your presentation, I think.
Yes. I'm not sure which list that went back to. So they are looking at, so elongated minerals is another issue. So apart from asbestos, the aspect ratio, so having greater than a 3-to-1 aspect ratio causes the particles to enter the lungs differently of the sizes. So that's actually another consideration that's being looked at as well. So those longer particles. So I am measuring particle shape as part of this characterization work.
Right. The next question is on characterization. So what are the main analytical methods you use for dust characterization? So if you want to just pick up that FTR, X-ray diffraction, etc.
So for what I'm doing, I'm actually using the MLA. So that Elaine and her group is running them out at JKMRC for me from the samples I've collected for the mines. So that is using the scanning electron microscopy with X-ray diffraction.
Okay, thank you. I was about to ask you if you could just give a bit of information on what the MLA was, and you answered that, so that's fantastic. All right, and then there's a follow-up one here from Mark, which is really looking at what are the health risks between amorphous and crystalline silica.
I'd have to look at the lung tissue data for that. I haven't been as involved on that side at this point. So it's and it's very interesting that the different mineralogy and the different size fractions are causing different things to happen to the lung tissue, and there can be some differences on what reactions you get with different types of lung tissue as well. I'm not as up on that side of things, but I'm basically trying to help some of the lung tissue people, because some of that of what they're using for samples is coal that's been crushed. But what we're finding in the characterization data when you actually collect a sample at a mine is it might not be just that coal. So we do need to look at the different particle size distributions and different chemical compositions that are being found in the respirable fraction, because they might not necessarily be representative of the seam.
Right. Okay, at the moment there are no further questions, Nikki, so I thought I'll give it a minute or two and then see if anybody's busy typing or got any other further questions. Right. Last time I started thanking the speaker, and as I was thanking them, the number of more questions popped up. So Nikki, I'm going to start thanking you, and if questions pop up, then I will stop. But Nikki, thank you very much for taking the time during your lunch break to come and give a webinar on this incredibly important topic on an incredibly important day, and we really appreciate that. And given the challenges that I think the world's facing on the health side, I think there's so much that we can do to increase and improve people's health and occupational health through good measurement, good monitoring, good hygiene, and maintaining physical distance. So I'd like to just thank you, Nikki, and everything of the best with your research. And we look forward to seeing the next series of information. And I'm always impressed at the level of analysis that we are now able to do. And as we analyze and scrutinize these samples further, I think we find out so much more that we hadn't considered. So Nikki, thank you very much. There are no further questions. So I'd like to just end the webinar there. Thank you.
Okay, thank you.